Hello everyone. So the topic of today's session is Zener diode based voltage regulators, which is AC to DC conversion. So we have the AC signal to 20 volts 50 hertz at the plug points, and we wish to get a DC voltage from it. So the basic circuit that does it is a half wave rectifier with a capacitive filter. So we get a DC, but the issue is it has a lot of ripple. So the first cut idea is to have a full wave rectifier so that the ripple is reduced by half, or use higher values of RNC in order to reduce the ripple. But what if we want to reduce the ripple even further without using higher values of RNC? So what we can do is we can incorporate something that is called as Zener diode based voltage regulators. So the basic idea is we take a Zener diode and we take a resistor, and we ensure that the Zener diode is biased in reverse bias mode, so it's such that it draws a minimum current of IZ minimum, so that this is biased in reverse bias condition and this voltage is VZ, so that we can drive the load resistor with a current of VZ by RL. And since the IV characteristic of the Zener diode is something like this in the reverse bias mode, this here is VZ and this here is IZ minimum. The advantage is that this slope is close to 90 degrees, meaning that even when the current changes, this voltage doesn't change much, which means that the ripple on VZ is low. So this is a low ripple circuit, because the thing is IZ minimum can have fluctuations, but fluctuations in IZ minimum or fluctuations in the Zener current are converted to the Zener voltage because of this slope. If there are fluctuations in the current, then there will be fluctuations in the voltage. Let's say if we have a ripple on IZ minimum, or we have a ripple on the current flowing through the Zener in this direction, then that ripple will be converted to a ripple in the voltage across the Zener, which is our regulated voltage. But the thing is, even if we have a ripple on the current through the Zener diode, the reverse bias current through the Zener diode, because of the fact that this slope is almost close to 90 degree, any ripple or change in IZ minimum will not be reflected in VZ to a very large extent, because VZ will fairly remain constant due to this 90 degree slope. So even if we have a ripple on IZ in this direction, the ripple on VZ will be low. So we will have a fairly regulated voltage. Now the next issue is, how do we bias the Zener in reverse condition, because we need a current in this direction for the Zener to be operated in reverse bias, and we need to supply this current to the load. So there must be a current source at the top that can support the KCL at this equation. So we have a current source, and that current source is equals to the current through the diode plus this current, which is VZ by RL, provided the diode is in reverse bias, meaning IZ is greater than IZ minimum. So how do we implement this current source is the next question. So in order to implement this current source, what we can do is we can take this voltage that we generate from a full wave rectifier circuit. So let's say we had a 12 volt RMS signal by some transformer, so that we can generate about 12 root 2 minus VD on approximately 16 volts of pulsating DC voltage. And this ripple is low because we choose good enough values of RNC, and we choose full wave rectifier instead of half wave, so that we have a decently good 16 volt battery, which is coming from a full wave rectifier circuit. Now we give it to a resistor, and we implement this current source by this resistor as shown. So what happens is, this voltage is fixed at VZ, this is 16, and this is R. So the I naught mentioned above becomes 16 minus VZ over R, and this can now support the IZ minimum as well as RL. And the maximum value of IL that you can draw will be I naught minus IZ minimum. So when the Zener draws minimum current, then you can supply maximum current to the load, or you can drive smaller loads. So the load that you can draw, the maximum that you can draw, this is the maximum current, and the minimum load that you can drive will be Vz over IL maximum. Now the next thing is, how do we increase the driving capacity? That is, how do we increase IL max and how do we reduce RL minimum? So the only thing is, you reduce the value of R. So on reducing the value of R, I naught increases, and when I naught increases, this remains constant at IC minimum, this can go up. So this remains constant and this can go up, so you can have higher value of IL maximum, and thus, since this is higher, this is constant, you can have lower values of RL minimum. So you can drive lower resistances. But the issue is, when there is no load attached, that is when the regulator is just kept in ideal state, all of this I naught will flow through the Zener. So you should ensure that the value of R should not be too low. You should ensure that I naught times Vz should be lesser than the power rating of the Zener, because when the regulator is not working, RL is infinity, so there is no current that flows here, so all of the I naught flows through Zener. So I naught into Vz, because when I naught flows through Zener is in reverse bias, because the current through Zener is in this direction. So this voltage is Vz, so the power across the Zener is I naught Vz, so this should be less than the power rating. So you cannot choose R to be arbitrarily low or I naught to be very high, because then that would pose a threat on this Zener being burned. So this is how you can make a voltage regulator. Thank you for watching.